Hello, my name is Huacheng. I'm currently an associate research scholar at Princeton University. I participated in the ICPC World Final 10 years ago in 2010 for the Tsinghua University team. It's a great pleasure to come back and talk about something in theoretical computer science that I thought many of you would be interested in. In this talk, I will talk about a subfield called succinct data structures. I guess we all know what is a data structure, and before I explain what succinct means in this context, let's first look at a motivating example. So let's look at this data structure problem called static partial sum. It's also called the rank problem. In this problem, we are giving a 0-1 array A of size n, so it has n entries, and each entry is a bit 0 or 1. And we would like to preprocess it into a data structure supporting the rank queries. So in each rank query, we get an index I, and we would like to know what is the number of ones in the first I entries. So what is Si, which is defined to be A0 plus A1 up to A of I minus 1. So I guess for this problem, the straightforward solution is just to store all the prefix sums S1 up to Sn. So this straightforward solution has linear preprocessing time. It uses space n, and it also has query time constant. So it is a very simple solution, but if we think about it, this problem is actually not fully solved because the space usage of this solution is actually not optimal. So in this for this problem, in this data structure, we need to store n sums, and each sum takes log n bits to encode. So in total, the space usage is actually n log n bits, but the input array A itself only has n bits, and there's a gap of factor of log n. So now the question is whether we can improve its space. So I guess one trick that is useful in practice and also in programming competitions is the bit packing. It turns out that this is also useful here. So we can use bit packing for this problem. So we divide the input array A into blocks of 64 bits, and then we're going to store each block in one 64-bit variable. So the entire input will be stored in an array of size n over 64. Then we're going to store the prefix sums of the blocks. So in other words, we're going to store how many ones are there in the first 64 bits, in the first 128 bits, in the first 192 bits, and so on. And we store all those bits, these sums in the data structure. And to answer our query I, we are going to first find which block contains this query, and then we're going to retrieve from the data structure the number of ones in all its preceding blocks, the one entry in the data structure that we store, and then we're going to retrieve the block that contains this query I, and then we're going to use pop count to count the number of ones preceding I within this block. So pop count is a CPU instruction that is also often offered by many programming languages. It basically counts the number of ones in a variable in constant time. And then in this case, we can just simply zero out all the irrelevant bits after I, and then use the pop count to count the number of ones before I within this variable. So using bit packing, we can solve this problem in constant time. And the space usage is a bit better. It's n log n divided by 64 because we only need to store n over 64 different sums in total. So asymptotically, the space usage is still n log n, but we save a factor of 64 in its leading constant. So now if we think about this problem and this data structure, there seems to be something wrong when we're talking about the asymptotic behavior in this setting. This is because each variable we assume that only has 64 bits, but we are letting n go to infinity. So that means we cannot even store the index I in one variable. The index I takes log n bits to describe, to encode, and in order to understand what the query is, it would take more than constant time. So what is a more realistic model that people study? So in theoretical computer science, a more realistic and general model that is used in this context is called the RAM model. So approximately, we can think of it as C++ programs with W-bit variables. Now W is not necessarily a constant like 64, but a variable that could potentially increase as n increases. And formally in this model, this parameter W is called the word size. So we essentially can process W bits in parallel in constant time, but only in limited ways. For example, we can add to W bit integers, or maybe do bitwise operations like bitwise AND or XOR or bitwise shift, and so on. And a common and realistic assumption for this model is that the word size is at least log n, so that the value of n can fit in one variable. And also for other problems where we use a polynomial space, it means that the pointers within this space can be described using O of W bits, which is a constant number of variables. And this setting of parameters is also what happens in reality. The Intel CPUs were 4-bit initially in the 70s, and later they became 8-bit, 16-bit, 32-bit, and now 64-bit. As the computing power and the memory size increase, or in other words, the maximum n the computers can handle increases, the word size should also increase accordingly. And in general, the larger the word size is, means that the stronger the model of computation is. So in constant time, it can do more things. And for this talk, we just think W being the minimum requirement, the minimum possible value satisfying the above requirement. We think W is some constant times log n. Okay, so now we think about programs with log n bit variables. Let's reanalyze the previous solution using bit packing. So the earlier solution actually now first stores the original input in variables, which takes n bits still, but now it only stores n over W prefix sums for each block, because each block now has W bits. So the total space becomes n plus n log n divided by W. Since W is on the order of log n, the total space usage is linear in n of n bits. And it is optimal up to a constant factor which is greater than 1. So now the question is whether we can further improve it. For example, can we achieve space 1 plus little of n bits of space and with roughly the same query time? So in other words, can we have a leading constant that approaches 1 as n goes to infinity? So before I answer this question, so let's first come back to the title, Succinct data structures. So it is exactly the subfield where people study this type of data structures. So for data structure problems with h bits of input, a data structure is called succinct if this data structure uses h plus little of h bits. In other words, it uses little of one fraction of extra space. And in this field, we study whether such data structure with low query time exists for some problem, and if they do, we would like to understand the trade-off between this little of h extra term and the query time. So it's important to notice that h here doesn't have to be the actual number of bits in the input. Instead, h is defined to be the minimum number of bits used necessary to represent or to encode the input. So let me give you a few examples. For example, when the input is an n-bit array, I guess it's clear that this h, the minimum bits required to represent the input, is n. And when the input is a set of size n with elements from 1 to m, there are probably many different ways to describe such a set. Maybe you encode the elements one by one, or maybe you store an indicator vector of the set. But the point is, in total, there are m choose n different inputs of this kind. So if we just want to encode the input without caring about the query time, then this can be done using log base 2 of m choose n bits. So h is, in this case, is this value. And when the input is an unlabeled binary tree of size n, by standard recurrence, we know that there are C of n different such trees, where C of n is the nth Catalan number. So in this case, the optimal space h is defined to be log base 2 of C of n, the Catalan number. And there are more examples. Okay, so now let's turn our attention back to the rank query problem. So it turns out that for this problem, there are succinct data structures. Succinct data structure for it exists. And next, I will present a succinct data structure for this problem by Jacobson in 1988. This data structure is going to use n plus O of n log n divided by log n bits of space. So the actual term is little of n term, but it's very close to n, but it is still little of n. And this data structure uses constant query time. It can answer each rank query in constant time. And it's worth noting that this is actually one of the very first succinct data structure studied in the theory community. So since this data structure actually appeared in the paper that introduced the concept of the succinct data structures by Jacobson. So how does it work? So the main idea is to use a two-level indexing structure. So before we divided A into blocks and then store the prefix sums of the blocks. Now we are going to divide A first into blocks, which now will have size log n squared. And then we further divide each block into chunks of size W, where W is the word size. And then in the data structure, we are going to store three parts of the data. So one, we are going to store the prefix sums of all the blocks as before. And then we're going to store the prefix sums of the chunks within each block. And then we're going to store each chunk in one variable directly. So let's see this data structure, this construction in detail. So how does it work? So we get this input array A. Then we're going to divide it into blocks, these green blocks, as you can see in the picture. And then we're going to divide each of these green blocks into chunks, which is separated by these brown borderlines. And then each block will have size log n squared, and each chunk will have size W. And then in the data structure, we first store the prefix sums of the blocks. So how many ones are there in the first block? How many ones are there in the first two blocks and the first three blocks, and so on. And then we store the prefix sums of the chunks within each block. So for each block, we're going to store how many ones are there in the first chunk within this block, how many ones are there in the first two chunks within this block, and so on. And finally, we're going to store all chunks separately, each chunk in one variable. Okay, now let's see how much space does this data structure use. So for the first part of this data structure, we have n over log n squared different blocks, and each block takes log n bits to encode the prefix sum. And then we have in total n over w chunks. But now the point is, for each chunk, the number of ones within the block preceding this chunk takes only log n bits to encode. So in total, for the second part of the data structure, it takes n over w log n bits. And finally, we need to store all the chunks in the data structure, which takes n bits exactly. So summing up these three parts of the space, we get n plus O of n log n divided by log n bits in total, as we claimed earlier. So how do we answer a query? So giving a query I, we first determine which block contains this I. Then we are going to retrieve the prefix sum of the blocks preceding this block, which is stored in the data structure. And then similarly, we are going to determine which chunk contains this query, and then we retrieve the prefix sum of the chunks preceding this chunk within the corresponding block. And finally, we are going to retrieve this chunk itself, and then same as before, zero out the irrelevant bits, and then use pop count to count the number of bits, number of ones preceding this query within this chunk. So the total query time is still a constant. So I guess a natural question now to ask is whether we can further improve the space. And a related question is, do we get smaller space, lower space, if we allow a slightly larger query time t? Maybe t is a larger constant, or it's slightly super constant. So I guess maybe one natural idea here is that instead of having chunk size being w, we can have chunks of size t times w. So this will improve the bound by a little bit. So now we only have to store n over tw different prefix sums for the chunks, and the total space, if we carry out the calculation, becomes n plus n log n divided by t log n. So when t is low, the actual space usage is still very, very close to n. Okay. So far, we have seen three data structures. So in the first data structure, the straightforward one, which uses direct storage, it uses n log n bits of space in total. And then the second data structure, we divide into blocks, which uses essentially one level indexing, and it uses a linear amount of space with a leading constant greater than 1. And in the third data structure, we just saw we divide the input into blocks, which was further divided into chunks, and it's a two-level indexing, and this achieves succinct space. So maybe a natural thought to improve the space usage here is that what happens if we use more levels? Say if we use what happens if we use t levels? So can we do better in this case? It seems that there is no reason why to stop to improve at 2 levels, right? So apparently, if we implement this idea naively, this is not going to work. So why this is the case? Suppose we are going to do this, and the lowest level chunk has size b for some parameter b. So first, if we want query time to be a constant, then this value of b must be at most O of w, because those are the chunks, those are the parts of the input we directly store, and we have to retrieve all of them to count the number of ones preceding the query. So b has to be at most O of w. But on the other hand, in the second lowest level, we have to store the number of bits preceding this chunk within that block. That takes at least log b bits per chunk. So in total, the extra space, if we calculate in this way, that would be at least n log b divided by b bits. And because b is at most w, this is at least n log n over log n up to a constant factor. But it turns out that this idea can be made to work if we do it very, very carefully. So the reason why the previous argument says that we cannot do this, we use the extra log b bits per chunk. This is because in the previous argument, or in the previous data structures, we implicitly stored the sum for each chunk twice. So what do I mean? In the first place, we store all the chunks directly in one variable, and implicitly the information of how many ones are there in this chunk is stored in this variable. And also we store the prefix sums within the second lowest level of the prefix of among the chunks. And from those prefixes, prefix sums, when we take the difference between the two sums, we also get the number of ones within each chunk, how many ones are there in each chunk. So because this exact same information of log b bits is stored in two separate locations in your data structure, so intuitively this is wasting space, and this wastes log b bits of space per chunk. So the idea to improve space is to store each chunk without implicitly storing the sum for the second time. And in total, we wish to use approximately b minus log b bits. So that means we know that the sum of the number of ones in each chunk was already stored elsewhere in the second lowest level of this indexing. And here we are going to just store this chunk without saying what the sum is, using b minus log b bits, so that at the query time we can first recover the sum from other parts of the data structure and then read off these b minus log b bits. And by combining these two pieces of information, we'll be able to recover the sum. And this is the main idea, and this needs to be implemented extremely carefully, and it also needs a few extra clever tricks in order to make it work. And the actual construction is also very technical, and I will skip the details in this talk. And also, as you may expect, because now we have t levels of indexing, so the query time will become proportional to t. And this idea of t-level indexing was proposed and also carried out by Petrascu in 2008. And in this data structure, it was actually achieved the space of n plus n over log n over t to the power of t. So it has an exponential dependence on t, and then plus O of n to the 3 over 4 extra bits for technical reasons. And the query time, as we mentioned earlier, is linear in t. So now if we want constant query time, we can set t to be some large constant, and we can achieve extra space being n over polylog t, log t to some constant for any large constant. And if we want extra space to be n to the 0.99, then the query time can be log n. And it turns out that there's a way to slightly improve the dependence on t, and it was shown in a recent paper by myself in last year, and it improves the space bound to n plus n over log n to the t plus n to the 0.9 bits. So the dependence on t becomes better, and also query time is also O of t. And now, if we want the extra space to be n to the 0.99, then the query time becomes log n over log n, and this is asymptotically better than the previous one. And to make such an improvement, the data structure applies an interesting connection to something called non-negative tensor decomposition. But in this talk, let me just skip the details. And it turns out that there's an impossibility result by Petrescu and Viola in 2010. So such impossibility results, or lower bounds, is actually a very different aspect of theoretical probability science from what is typically appeared in a programming competition. So in this area, people mathematically prove statements that, like, it is impossible to have a data structure that is too efficient. And in this case, they prove that any data structure that has query time t must use space at least n plus n over log n to the t. So up to a constant factor in the query time, the dependence on t is actually optimal. And this concludes the first part of my talk. And from now on, let's look at a different problem. This problem is called storing base B vectors, and it was studied more recently. So let's look at what this problem is. So in this problem, we're giving an array A of size n, where each entry is not a bit anymore. It is from a larger alphabet of size b. It's between 0 and b minus 1. And we would like to preprocess this array into a data structure supporting retrieval queries. In each query, we get index I, and we just want to know what is AI. And here we assume that this value of b is at most 2 to the w, so each entry of this array can fit in one variable. So I guess for this problem, there are b to the n different possible inputs, so the optimal space just to store the input without worrying about the query time is n log b bits. So now you may wonder, what is the point of this problem? Can't we just store each AI using log b bits and then use bit packing so that the total space is n log b? So the point of this problem is that b is not necessarily a power of 2. So this straightforward solution actually uses n log b bits base 2 with a ceiling on the factor of log b. So in general, this space bound can be h, the minimum space, plus O of n bits. For example, when b is equal to 33, then we have to use 6 bits per entry, which is 2 to the 6 is 64. That is 6 n bits, whereas the optimal space for this data structure is almost 5n. And the goal is to use very, very close to n log b bits with the ceiling outside the product, not in the factor for each entry of this data structure, for each entry of the input. And it turns out that there is a way to do this. So a data structure proposed by Dodis, Petrescu, and Thorup in 2010 solves this problem with almost approximately h bits, and it also achieves a constant query time. And we'll see what the exact space is later. So before I explain what is the exact data structure, let's first look at a special case of this problem, in which case the description becomes much cleaner. Then we will extend it to the full version. Okay, so now let's first assume that the word size is an odd number, and then we'll assume this value b, the size of each entry, is 2 to the w minus 1 plus 1. So b just has one extra possible value to fit in w minus 1 bits, and then we assume n is not too large. It's at most 2 to the w over 8. And then if we naively store each AI in an array, then we're going to use n w bits in total. But we are going to show that we can actually do this using n times w minus 1, then plus 1 bit. So in total, we use 1 extra bit before multiplying it with n. Okay, so how does it work? So we first, for simplicity of notation, let's let t be 2 to the w minus 1 divided by 2 be an integer power of 2. So b would just be t squared plus 1. So we get an array such that each entry is from a set of size t squared plus 1. And the first thing we do is going to break the first integer, the first entry of this array, into a pair of integers from sets of sizes t and t plus 1 respectively. So what do I mean is we're going to break a0 into a pair x and y such that x is set to a0 mod t and y is set to a0 divided by t rounded down. And note that this operation is invertible in the sense that if we see the pair x and y, then we can reconstruct the original input a0. So we are not actually losing information by doing such a transformation. And because the product of t and t plus 1 is at least t squared plus 1, so we'll have the value of y being at most t plus 1. So x is between 0 and t minus 1, and y will be between 0 and t. So after we break the first integer, we get n plus 1 integers in total. Next, we're going to break the second integer similarly, but into two numbers from different ranges, from ranges of size t minus 1 and t plus 2 respectively. And similarly, because the product of these two numbers is still greater than t plus 1, and this is guaranteed to be possible. And in general, we are going to break all the integers into a pair, such that the ith integer is broken into two integers from ranges of size t minus y and t plus I plus 1 respectively. So far we haven't done anything interesting yet. We just broke each entry of the input into a pair, and the interesting part of this construction is actually in the last step, where we regroup these integers into pairs and then combine them. So we are going to take the second component of the first integer of size t plus 1, and the first component of the second integer of size t minus 1, and then we are going to combine these two integers into one single big integer from range of size t squared. So how is this done? We're going to combine x and y into an integer wi, and wi is just computed by x plus y times t plus 1. And it's also easy to verify that this step is also invertible. And because the product of t minus I and t plus I is smaller than t squared, so this can always be done. So the value of wi, the outcome, is always smaller than t squared. Okay, so as a short summary, as a quick summary, so what has happened in this data structure in the pre-processing step so far, we get an array of size t squared plus 1 for each entry. We first break each entry into a pair of integers of different sizes, and then we regroup them and then recombine them into integers. And the point here is that now in the outcome, the size of each integer becomes just one smaller. So now they are coming from a set of size t squared. So equivalently, we squeeze out one bit of range from each AI and then fuse it into the next entry, and the size of the ranges being squeezed out accumulates and is finally added to the last entry. And the point of doing this is because t is a factor of is a power of 2, and t squared is also a power of 2, and we eliminated the one extra value so that they can fit in an integer number of bits. So in the final data structure, we're just going to store each t using w minus 1 divided by 2 bits, and each t squared using w minus 1 bits. And then we're going to rearrange and bit pack them into w bit variables. And also the last integer will be stored, will be rounded up and stored straightforwardly. So the total space usage of this data structure is w minus 1 divided by 2 bits for the first t, and w minus 1 bits for the n minus 1 t squares, and also w minus 1 divided by 2 plus 1 bit for the last integer. And if we do the calculation, this turns out to be exactly w minus 1 times n plus 1 bit as we claimed. And because the optimal space in this case for this setting of parameters h is n log b, which is more than w minus 1 n bits. So this data structure actually uses the optimal space h rounded up n bits. Okay, so so we have analyzed this space. So how do we retrieve one entry of the input? I guess the query algorithm is quite straightforward. So let me just go over it quickly. So to retrieve one AI from range of size t squared plus 1, we first find out, first observe that it suffices to retrieve the two smaller integers from ranges of size t minus I and t plus I plus 1 respectively. And then it suffices to retrieve the two integers we stored directly in the data structure of size t squared. And because those two integers are directly stored in at most 3 consecutive variables in the final data structure, so the query algorithm will first find out which bits in the data structure we need, and then retrieve those bits in constant time, and then recover those two integers, which are at most t squared, and then from them we are going to reconstruct the two integers, which are at most t plus I plus 1 and t minus I respectively, and then finally use these two integers to recover the original input AI. And the query time of this query algorithm is constant. Okay, so now let's turn our attention back to the general problem for general B. So first we can think about B. We can, without loss of generality, assume that B is at least 2 to the W over 2. This is because if B is smaller, then we could find some integer B, such as integer D, such that B to the D is at least 2 to the W over 2, and then group D entries into 1. So basically we view these D entries as an integer in its base B representation. Okay, so now B is at least 2 to the W over 2. And the high-level approach of this data structure by Dodis, Piotrowski, and Thorup is very similar to the solution I just showed you, to the data structure, So we're going to first decompose each entry of this array into a pair xi and yi, but now from ranges of different sizes, of sizes pi and qi respectively, and then we are going to merge, regroup these small integers into large integers. We're going to merge yi and xi plus 1 into one integer wi as before. And then in the final data structure, we're just going to directly store x0, the first x that is not merged, into any w, and then store the n minus 1 values of w, and then we're going to store the last y that is not merged. So the goal of this idea is to find these two parameters, these two sequences of parameters pi and qi, such that b is smaller than the product of pi and qi, but it will be very close to this product so that it doesn't waste much space. And also the product of qi and next pi plus 1 should be smaller than, but very close to some power of 2. And in the example we saw earlier, pi was set to t minus I, and qi was set to t plus I plus 1. Okay. So in general, one way to generate these sequence of pi and qi is by induction. So we can inductively calculate pi and qi as follows. So in the base case, we are going to set p0, the first p, to be a power of 2, such that it is between square root of b and 2 times square root of b. So there's always such a power of 2 exists in this range. Then in the inductive step, suppose we already generated the value of pi, then the next qi will be set to b divided by pi rounded up. And then giving so this value is set so that the product of pi and qi is greater than b, but this is the smallest value of q that satisfies this requirement. So this makes the space loss minimized. And giving a value of qi, we're going to set the next pi such that the value of pi plus 1 is going to be in the same range. It's between square root of b and 2 times square root of b, and it has the form that it's a integer power of 2 divided by qi rounded down. and it's not very hard to verify that such pi plus 1 always exists. So to see how much space, so this generates the two sequences, pi and qi, and we can carry out the earlier argument and data structures. So to see how much space it actually uses, we can write down a formal analysis by writing down the space and then simplifying the equations and then obtaining the final bond. But let me not do this on the slides because this is going to be very technical. And instead, let me just show you informally why this data structure is going to use good space by setting pi and qi in this way. And what I'm going to say can be made formal. So in this data structure, there are three parts that loses space. One is we're going to store the value, the last qi, the last integer directly, and the qn minus 1, that this is not necessarily a power of 2, so we're going to waste at most 1 bit by storing that. And that only happens once, so that in total it's 1 bit. And also, the second is that we're going to represent an integer in a range of size b by an integer in a range of size pi times qi. And b is smaller than pi times qi, so intuitively this wastes space because in this range we could have stored an integer with we could have stored more information. So intuitively, the former range range of size b, an integer in this range is going to take log b bits, and the integer in the later range of size pi times qi can be described using log base 2 of pi times qi bits. So if we take the difference, this is how many bits we waste by representing some small object using a large amount of space. And it turns out that the difference is log base 2 of pi times qi divided b. And if we do the calculation, this turns out to be log base 2 of 1 plus pi divided by b. Then by the fact that log of 1 plus epsilon is theta of epsilon, this is roughly theta of 1 over the square root of b, because we always set pi to be roughly the square root of b. And similarly, there's also a part that we lose space, where we store integer in range of qi times pi plus 1 by an integer in range of 2 to the ti. And by a similar calculation, we can show that each time we do this, we waste a space of roughly 1 over the square root of b bit. And in total, this is going to happen of n times. So the total space loss for the second part is at most n over the square root of b. But according to the setting of our parameters, this is going to be smaller than 1 bit. So in total, we are going to waste at most 2 bits. So, okay, now how do we answer a query? So it turns out that there's an issue with this approach because the query algorithm, in order to answer a query, needs to know all these parameters, pi and qi. But in general, these pi and qi may not have a closed form if they are generated in this way. And we need to pre-compute a linear number of constants, which is too expensive to store in the data structure. And in the solution by Dordis, Petrasco, and Thorup, they showed that it is actually possible to reuse many of the constants by building a tree structure instead of just storing this sequence in the linear order. So in fact, by doing that, we only need O of log n constants, such that the query algorithm can still recover one entry by using only a constant number of them. So this means that we can actually afford to pre-compute and store as a part of the data structure these log n constants, and then when we need some of them, we just retrieve those constants from the data structure. And the space in this case becomes h plus log n squared bits. The one observation in a very recent paper by myself implies that there's a different way to get these pi's and qi's such that they become efficiently computable, and there's no need to pre-compute anything. And it is based on a very different intuition which pre-estimates how much each range is squeezed out from each AI, and then computes the corresponding pi according to that. So due to the lack of time, let me not explain all the details here. But the conclusion is that we could set pi to be this quantity, and then also set qi to be b over pi rounded up. And it's not very hard to verify that this can be computed by the query algorithm giving I in constant time. Okay, so finally, let me list a few more problems with Succinct that people have studied which have succinct data structures. So the first problem is also by Jacobson. So the input of this problem is that we have a sequence of n pairs of balanced parentheses, and in each query we would like to know what is the matching parenthesis to the parenthesis at position p. So we can use recurrence to show that to calculate that the total number for inputs to this problem is the nth Catalan number, which turns out to be roughly 2 to the 2n divided by n to the 1.5. So by taking the logarithm, the optimal space for this problem is roughly 2n minus 1.5n. So Jacobson's data structure uses 2n plus little of n bits, which is succinct. And the second problem is very related to this question. The input is a binary tree with n nodes labeled from 1 to n according to the in-order traversal of this tree. And the query each query we're given two nodes, I and j, and we would like to ask what is their lowest common ancestor. And this problem is actually equivalent to the range minimum query of an array of size of length n. And again, by calculating how many, we can calculate how many inputs are there, and it turns out to be also the nth Catalan number. And it turns out for this problem, we can also get space, which is 2n plus little of n, and little of n being n over log n to the t bits. And this problem has applications to the longest common prefix structure in the suffix arrays, or the LCP structures in the suffix arrays. And also for the next problem, as an input, we get a sequence of n vertices of a graph. And the graph will have size k, and it's d-regular, meaning that every vertex has degree d, and for now we can think of it's an undirected graph, such that the consecutive vertices in the sequence are adjacent in d. So in other words, we get one vertex in the graph, and then we get one neighbor of this vertex, and we get another neighbor of the second vertex, and we get another neighbor of the third vertex, until we get a sequence of n vertices in this way. And the query asks what is the ith vertex in this sequence. The historian naively will take n log k bits, but the input takes only log k plus n minus 1 log d bits to encode by just specifying what is the neighbor. And in a very recent paper, we showed that it is actually possible to store this data structure using just a constant more bits than this minimum possible bits, and then still it allows us to recover the ith factor in this sequence. And the last data structure problem I would like to mention is called this indexable dictionary, and the input is a set of size n within a range of size m, and we'd like to preprocess them so that we can answer two types of queries simultaneously. So in one query, rank query, we're getting one element x from this set, from this range of size m, and we first would like to detect whether x is in the set or not. If it is not in the set, we must return -1. Otherwise, we must return the number of elements that is at most x, so the rank of x. And the second query is select I, which is the inverse of the rank queries. Given this index I, we'd like to return the ith smallest element in the set. And it was shown that you can do this, solve this problem also succinctly using little of n plus log m extra bits. So on this slide, I'm only showing a small number of examples, and there are many other problems that admit succinct data structures. Also, there are many other settings in which people study the succinct data structures, such as dynamic data structures. So I guess in this talk, I have been focusing on problems where the data is always fixed, but in general, we also study problems where the data can be modified, and we would like to maintain this data efficiently, but with succinct space. So let me conclude my talk by introducing to you my favorite open question in this subfield. It's called the dictionary problem. So this is very similar problem to the last problem we saw on the previous slide. In the input, we get a set of size n over a universe of size n, every element is between 0 and n minus 1, and the query would just would like to know if some element x belongs to this set. So this can be solved by, like, for example, hashing, and this is also an easier problem than the indexable dictionary from the previous slide, as we're only asking membership queries whether x is in the set. And for this reason, we could potentially do better, and in fact, there exists better data structures. So the best known deterministic data structure for this problem is by Pei and Petrescu, and it uses space log base 2 of m choose n, which is the minimum space possible, plus n choose log n to the t, plus O of log n bits. And if we allow randomization, a very recent work by myself solved this problem using log base 2 of m choose n plus n to the 1 over t plus iterative log of n iterative t times, so that each query can be answered in expectation in O of t time. And if we allow the query time to initialize, then we can even get the space down to log base 2 of n plus n choose n plus only log n to some constant. So initialization here means that before the query algorithm starts to answer any query, it first runs by itself for some time in order to pre-compute, for pre-computation. Then it may not, in this phase, it may not look at the data structure or any upcoming queries. And after it is initialized, it starts to handle queries, and each query then can be answered in constant time in expectation. And for this problem, there is no impossibility results known. So this means that it is potentially possible to use just one extra bit and answer each query in constant time, even deterministically. But obviously, the current bounds for the known data structures are very far from that. So the open problem here is whether there is a deterministic data structure for dictionary problem that uses much less than n bits of extra space and solves the problem with constant query time. And thank you for listening.